basically using the Fourier transform inverse to get the Dtft inverse, and that's a gift. That saves you a lot, because if you have to go through those calculations with the actual integration, it could be a monster of a pain. So we really use duality, the power of duality to get that. And let's see. Any questions at all? Nothing? Okay. How many did it really? One? One person did it? Oh, that's going to be a fun day. Did you not have any questions for, I mean, nobody did it except one person?
I heard EMAG.
You had EMAG today?
I had EMAG test today, yeah.
How many had EMAG test today? Well, you didn't do it. Did you do it? All right. Well, do it. Because some of that stuff's very important. I'm just warning you, some of the stuff is very important. Yes, yes.
I know you have put the solution for number 1 on there, like an A, B, C, D, right? I still have some.
All right. Tell me the problem exactly. I mean,
So it's
A, B, C, D.
A is x of omega equals
say it again. X of capital omega equal.
triangle function
Ah,
4 pi over 3.
4 pi here
Yes, over 3.
over 3. Keep going.
Of
That's it?
Yeah.
capital. Yeah.
That's it?
Yep.
Well, this one's sort of a gift. And the reason is we know if you have first the pulse function of tau, which is the rect function, right, in our book, of t over tau of t, that goes to tau times the sinc, right, of omega tau over 2. We also know if you have the triangle function of tau of t, that goes to tau over 2 times the sinc squared of omega tau over 4. Correct, class? So we see we have a triangle to a function. We have a functional form where we have a triangle in time goes to a sinc squared in the frequency domain, right? But we actually have what? A triangle in the frequency domain, right? So we're going to use duality. This is as simple as it gets. But I'm going to do with the continuous time Fourier transform first, then I'll go to the discrete time Fourier transform. How many understand what I'm doing here? Using duality for this. Be sure you do. So using duality, I can take this and stick it into the well, I'll go to the time domain first. When I take this function and go to the time domain, it becomes tau, right, over 2 times the sinc squared. Then it becomes t tau over 4, right? Then when we go this direction, what do? Using duality. Class? There's one thing that comes before all others. 2 pi. Make sure you say that. So I have 2 pi, right? And then it's going to be this triangle function, still with tau. But now, instead of t, what do I put in here? Minus omega, correct? In this function, can I leave it as plus omega, class? Yes, right? Sure. It's an even function. Is it a triangle function and even just like a pulse? It's symmetric about the origin. Do you all agree with that, class? Mm-hmm. Everybody? So now I'll just put omega here. Now I look at this, right? I'm going to divide by 2 pi. Follow me on this, guys? So I'll divide by 2 pi, and this makes this side 4 pi. And now I look at this. This is a general statement for any triangle function in the continuous time domain of with tau. It goes to that, right? Now we look at the actual triangle function. Here, tau is defined as 4 pi over 3, correct? That means the total span of it is from minus 2 pi over 3 to plus 2 pi over 3. Do you agree with me there? That is between minus pi and plus pi. Do you agree? In other words, the span of this is less than, right, minus pi to plus pi. That would be 2 pi. The span of this is 4 pi over 3. So therefore, we can go right to the actual what I showed you, using the continuous time Fourier transform pairing to get the discrete time Fourier transform. We can simply go from here and put down, not tau, but now 4 pi over 3, because that is the width of capital omega. And here, since here now tau becomes 4 pi over 3, I come over here, and what do I see? This becomes 1/3, right? Times sinc squared, but what does t become? N, right? So now it becomes n. Tau is still 4 pi over 3, divided by 4 is pi over 3. And that is a relationship. That's the inverse of that. I hope you see this. This is just a straightforward, no miss thing. If you know the continuous time Fourier transform pairings from frequency to time, and the span of that is between minus pi and plus pi, which it is, then you can simply take omega and turn it into capital omega and t and turn it into n. And it's that easy. And that saves a world of hurt doing those integrations, in my opinion. You don't have to redo them. Do you all agree with this, class? And we got there using duality. Remember, duality is the secret for all this. Is there any other question? We can do them all, but I mean.
On the next one, it was a graph.
I know, was that just shifted? Was it a triangle function shifted, or what was it?
It was
What was it?
It's basically a pulse minus the triangle.
All right, we'll do this one, just because I want to do one more of these things, since apparently between football and EMAG, people haven't sunk their teeth in on homework. For this one, is it centered about the origin or not? All right, so this is the capital omega domain, and this is my x of omega. This is where you're going to have to define it in terms of known functions. And where does it start?
2 pi over 3.
Minus 2 pi over 3. And is it symmetric to 2 pi over 3?
Yes, sir.
2 pi over 3 in the omega domain. Does it go like this straight down, or is it flat and then go down?
It goes straight down.
What?
Straight down.
All right, like this?
Yes. And that's the one that it goes up to.
Is this 1 here?
Yes.
Is that the function? How many see this is definable in terms of a pulse minus a triangle? All right, I'm going to just do this one so we all see it. This is easily defined as simply a pulse function, right? Of width what? What's the width? Right, 4 pi, right, over 3 of what? Omega, right? Minus triangle function of width 4 pi over 3 of omega, right? Now, we got this already, the second one, no? We've got this second part. Do you agree with me, class?
Yep.
We need the first part. How do we get it? Well, that looks like we could use duality from, right, these two, correct, class? Some of you know this. I'm going to just do this one time for completeness. So now, if we're doing this one, over here, I put tau, right? Sinc, not omega, but t tau over 2, correct? Remember, you replace omega with t when you're going this direction, right? And now when you go from time to frequency, the first thing you see is what comes out here? Remember, I want you to say it. It'll stay with you if you do. 2 pi, right? And then I put this function, right? But of, technically minus omega, it's an even function, becomes plus omega. Correct, class? You all agree with that? Right? Now, if that was a sine of like tau t, we couldn't do it because sine's an odd function. You can't do that. Right? But this is an even function, so we can do it. Then I divide by 2 pi. And then I look at that, and I see tau for that one is 4 pi. Its span is from minus 2/3 pi, or to plus 2/3 pi, which is within the minus pi to plus pi realm, right, class? So I can easily just say, I can just put this as 4 pi over 3. And then I can get rid of omega and make it capital omega. I can take this and make it 4 pi over 3, which makes this 1/3, doesn't it, class? And then I replace t with n. And tau is 4 pi over 3, correct? So I really have 2/3 pi here, don't I, class? Do y'all agree with that? I'm just literally, what? I'm putting tau in, replacing tau with 4 pi over 3 everywhere. Correct, class? And I replace t by n. And now we have the pairing here, so I can say the pulse goes to this, right? And the triangle function of width 4 pi over 3 goes to 1/3 sinc squared of n pi over 3, correct? Yes?
Isn't it 2/3?
That is 2/3.
The first part, you didn't.
What?
The magnitude.
Let me see, that should have been, that's tau over 2 pi, correct? All right, let's see, tau is 4 pi. Yeah, you're right, 2/3. I'm sorry, you're right about that. And so this function, and it's going to be minus, this is positive, then it's going to be minus the 1/3 sinc squared of n pi over 3. Right? And that would be it. Y'all agree with this? I'm doing this for a reason, make sure at least you see the method, so you can extend this to any type of pairings necessary. All right. Now, are there any other questions?
What would happen if that was like outside of the negative pi?
All right, let me just show you. That's a very good question. Suppose I gave you this. Suppose my functional form was this. Here's minus pi, here's plus pi. Now just listen, this is a hypothetical. I want you to listen to this. Suppose this is my x of omega, and it looks like this. Just like this. So it's symmetric about there. Stops at pi. And then it's 0. It's going to repeat itself. With the x of capital omega, it's going to repeat itself. You're going to see this, and then it's going to repeat itself every 2 pi. Do you understand that, class? So I'm just going from minus pi to pi. But suppose I have a transform. Now listen, I have a transform of a sinc function in the frequency domain. Let's just assume this is a sinc function from minus pi to pi. All right? Just assume that. Are you with me? Say absolute value of a sinc function. Follow me on that? I'm going to do right here. Well, suppose now I see that in the frequency domain, I know this is an absolute value of a sinc function, something like this. And this is the x of omega. And I say if it's an absolute value of the sinc function, it goes to some x of t. Don't worry about it right now. It's an absolute value of the sinc function that does have a transform. And I see it's exactly the same from minus pi to pi as this one, right? So I'm going to try to replace small omega by capital and t by n, but it's wrong because you notice this keeps going on outside the bounds from minus pi to pi. Do y'all see that? So you can't use this transform pairing to get this transform pairing because this only goes from minus pi to pi. Got it? Now, some of you are thinking ahead probably, and you're going to say, well, we can make that look like that. We can just multiply this by a pulse of with 2 pi times capital omega, right? Right? But you don't have that transform, right? You have this transform without the pulse. So when I multiply it by a pulse, what happens? Multiplication. I can say if this goes to this in the time, and I know the pulse will go to a sinc function in time, correct? Right? But now I have to do convolution over here to get the answer, don't I? If it's multiplication of frequency, it's convolution of time. And that is not an easy convolution. That's a mess. So what I'm saying is you could not use this information, this to get this one, because this only exists from minus pi to pi. This one has values that are non-zero outside that range. Do you see that, class? That's where it doesn't work. How many see that? It's important you do because people do that. They will say, well, look, minus 5 pi. Same thing, we'll just use it. Can't do that. All right. Any other questions? That's a good question, whoever asked it, because that's a legitimate thing. You haven't seen any functional forms you couldn't do, right? Now you do. Okay. All right. Today, we're going to keep going, but this time, we're going to get into the Dtft to the Dft, and then from, I'm not going to do FFT today, but I am going to show you how to compare an actual continuous time Fourier transform to a finite, what's called a Dft that I'm going to actually introduce right now. So let me go ahead and do this. Now take good notes here, because this stuff in the book, I don't know how well it's illustrated, so please listen to me here. I'm trying to do you guys a big favor. This is not easy. Well, it's not hard, but the book doesn't make it as easy, in my opinion, as it can be. First, I'm going to go ahead and just put down x of omega is equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt. That's the continuous time Fourier transform. Now when we go ahead and sample, right, instead of having a continuous time signal, it's a sampled signal, we end up with the Dtft. I'll just call it continuous time Fourier transform. Now a Dtft is x of omega, right, is equal to not an integration but a summation of n, or really n goes from technically minus infinity to infinity of x of n times e to the minus j n omega, right? That's the Dtft, right? Now what we do is say, what if we have a finite number of samples? Not an infinite number. You'll notice the sum on this goes from minus infinity to infinity. Still not something that the computer can technically do. Now I'm going to have a finite number of actual samples, not an infinite. And everything outside that finite number is assumed 0, or it's not even an issue. So now I'm going to say the Dft, that's discrete Fourier transform, is equal to x of k, not x of omega, just x of k. K is going to be an index. It has integer values from 0 to n minus 1, where n minus 1 are the number of samples. It's equal to the summation from n equals 0 to n minus 1, and capital N is simply the number of samples. And then it's x of n, and it's multiplied by e to the minus j 2 pi over n to the nk power. Now I'm going to tell you, just write this down. I want to explain something, why I wrote it this way. The book has it a little differently. Now when you look here, that omega, right? It repeats every 2 pi, correct, class? From minus pi to plus pi is the same as if you added 2 pi to that. If you have omega plus 2 pi, you get the same answer. Do y'all follow me? Now what this does is take that range, 2 pi, and it divides it up into n pieces. So if you have 35 samples, you would have 35, positions angularly spaced. You would have 2 pi, or what, 360 degrees divided by 35. Follow me? Now, then you have that to the nk power. Now, k is an index that has to do with this. So if you think about it, you chop that thing up into n samples, right? There's a DC component, which would be k equals 0. There's a component at k equal 1, which would be the next increment in frequency, which would be 2 pi over whatever n is, say 35, right? And then it would be to k equals 1. You'd still have to sum over n. I'll show you how to do this, right? Now this is something that you can calculate. And there's a very efficient method for doing this called the FFT. How many have heard of fast Fourier transforms, or FFTs? You'll be using them a lot. FFTs are a very efficient way to do this calculation that I'll get to later. But first things first, these are the forward transform. This is called the analysis portion. We're analyzing a waveform in all these. Continuous time, this is Dtft and discrete time, and then now in finite discrete time. This is doable. This is a computer can do this. I'm going to go ahead and put also the inverses right here too. For a continuous time Fourier transform, x of t was equal to what? 1 over 2 pi, the integral from minus infinity to infinity, right? Of x of omega times, small omega, e to the minus, or plus j omega t, right? D omega. Here, capital X, small x of n, the inverse of that, right there, would be x of n would be equal to, and now for this one, it's 1 over 2 pi, and it's the integral from minus pi to pi of x of capital omega, e to the j omega times n d omega. You all remember that? The integrations were identical in every method, every way except for the extent, the limits. Correct, class? And that's why we can do that duality business. For this one, x of n, finite value x of n, would be equal to 1 over capital N, the summation of, now it's going to be x of k times e to the, that was a minus, this becomes plus j 2 pi over n to the nk power. I like writing it that way. And here k will go from 0 to n minus 1. The summation on this one's over k. They're all doing the same thing. They're interrogating the signal to see how much of the signal, really the square root of the energy or power of the signal exists at each frequency. That's what they're doing. We're exploring what the frequency domain signature looks like of a function and all these things. It's a type of analysis, not synthesis. Now, the next thing I'm going to do is actually do a DFT to just show you what it is, okay, guys? You want to see it so you understand how to calculate. So let me do an easy one. I'm going to take x equal, and the way the book will do it, they'll have a curly bracket like this, and I'm going to go 1, 2, 2, 1. Now what that means, and I'll put a little bar under there. What does that bar mean if it's under a letter, under a number?
0.
That's the point where n is 0, right? So here, I'm going to go ahead and calculate the DFT of this. I'm going to say x of k in general is equal to the summation. Let me get that up a little higher. I'm just rewriting that. You don't have to do this. I'm going to say x of k is equal to the summation. N equals 0. How many values do we have here?
4.
So it goes from 0 to 4 minus 1 or 3. To 3 of x of n, and then it's going to be times e to the minus j 2 pi over n, or really minus j pi over 2 to the nk. That's how you do this. Now, really, what is that? 1, or e to the minus j pi over 2 is e to the minus j 90 degrees, isn't it? It's really minus j, isn't it, class? Here's the way you think about this, and it'll help you. I'll try to show you it right here. The way you think about this is if this is the real axis, and this is the imaginary axis, then if I have e to anything, in this case, this is like e to the j theta, where this is theta. Well, if it's e to the minus j pi over 2, then you go this way. This would be e to the minus j theta, whatever theta is. Follow me? Where this length will be 1. Do you follow me on this? So if it's e to the j pi over 2, that's j, right? This is the j-axis. If it's e to the minus j pi over 2, it's minus j. E to the minus j pi is minus 1. This would be minus 1. And this would be plus 1. Do you all see what I'm doing here? Now follow me on this one. So when we go over here, we're going to calculate x0. That's when k is equal to 0. What do you notice about this term when k is equal to 0? 1, isn't it? Anything to the 0 power is 1, so I'm adding up the values of x of n, right? That's all I'm doing. X of 0 is just adding them all up, which is 6, isn't it, class, by inspection? How many see this right? Just add them up, 6, right? What do you see next? X of 1. I'm going to write it down. That's going to be the summation where n equals 0 to 3 of x of n. I'm just going to leave it as x of n. Times, now it's e to the minus j pi over 2, right? To the n power. K is 1 on this one. Follow me? If k is 1 here, it doesn't do anything, really, does it? So I'm going to take this. Now notice, this is what? 1 at an angle of minus 90 degrees, correct? Or minus j. So if I go ahead and do this, I take x of 0 times 1, which is the first value, 1, right? That's 1. E to the 0 is 1, correct? Plus what? Then a 2, right? Times e to the minus j pi over 2 to the 1 power, or e to the minus j pi over 2. What is e to the minus j pi over 2? Say it. E to the minus j pi over 2 is minus j, isn't it? Isn't it that? Remember, the hands of the clock would be down here. It'd be minus j, correct? So I'll just put a minus j2 here. Now you can see what's going on. The next time, the hands of the clock wind here for the next term, right? So now the next term is going to be what? Plus 2, right? But what is e to the minus j pi? Because I got n equals 2, right? What's e to the minus j pi? Minus 1, or this becomes minus 2, correct? Y'all with me? Final term, what? Yeah. Sure. This is, when this term, when n equals 2, I have e to the minus j pi over 2 squared, remember? And the 2 can just come in there, so the 2's cancel. It's e to the minus j pi, or e to the minus pi is, minus j pi is really, what, 180 degrees, or right? E to the minus j pi over 2. What I'm doing is winding the clock. First time I take it, when n is 0, it's here, that e to the j pi, or pi over 2 to the n pi, right, is there, when n is 0. N equal 1, n equal 2, n equal 3, it's j. You can see what's happening. Do y'all see this one? So the last term is what?
J.
Plus value is 1, right? Times this to the third. So it's really e to the minus j pi over 2, or e to the minus j 90 degrees 3 times. 0 goes. 1 is minus 90, 2 is minus 180, 3 is minus 270, or plus 90, or j, isn't it, class? So I can just put plus j. Whoever said that before is absolutely right. So what's this value? 1 minus 2 is minus 1, right? J minus 2j is minus j. Do you all see that, class? So I can say this one is that, that's x of 1. What is x of 2? Well, now I have the summation. N equals 0 to 3, x of n, and now what do I got? I have e to the minus j, what? Here, k is 2, isn't it, class? Which means, what do I get? If this is 2, don't I get e to the minus j pi to the n power? Sure. I have e to the minus j pi to the n power. Now that's what? At n equals 0, this is 1. N equal 1, it's minus 1. N equal 2, it's 1. N equal 3, it is minus 1. So this is what? This is going to be the first number 1, right? Minus the second number 2, correct? Plus the third number 2, minus the fourth number 1, which is
0.
0. Agreed? With me on this? I'm just turning the crank. Finally, what's x3? Try this one on your own. N equals 0 to 3 of x of n, right? And then here I have e to the minus j. Now what is that going to be? When k is 3, I have minus 2 pi over 3, or I'm sorry, 3 halves pi, right? To the nth power. Now what is that? Think about that. Well, Here's when it's 0, e to the minus j pi over 2, e to the minus j pi, e to the minus j 3 pi over 2. Do you agree with me? Which is j, isn't it, class? Do you agree with me? By the way, every time we increment n, we're going to go all the way around through. We're going to go 3 times. So the next value, e to the minus j 3 pi over 2 would be 1, 2, 3. It would be minus 1. Follow me? So just work with me on this. So what do you get? The first value is always going to be the same. It's 1, isn't it? It's just the first value of your series if it starts at 0. Correct, class? What's the next value? Then I take plus 2 times what? Now it's plus j, isn't it? Started at, it's going to be, when this is 1, right? I have e to the minus j 3 pi over 2, right? So that's, I mean, if you think about it, I start here at 0, then that's minus j pi over 2, minus j pi, minus j 3 pi over 2, or plus j, isn't it? So this is plus j, so it's plus 2j. Do you agree with me, class? Keep going, what's the next value? 2, right, times what?
Minus 1.
Now this is going to be 2, isn't it, class? Isn't that minus 1 right there? All right, you're right. So it's going to be minus 2. What next? Keep going. Finally, the final value is plus 1 times what?
J.
Now n is 3, pardon me?
J.
Minus j.
You're right. Whoever said negative j is right.
Yeah, minus j.
Minus j, you're right. Minus j. And what's that going to be? That's going to be, we got minus 1 plus j, right? And that's it. Understand, class? Now, if we want to do the inverse Dtft, which is this, we take the values of x of k that we established here, and we just do the reverse. Are you with me? It's basically an exercise in bookkeeping. Once you understand what the formulas mean, it's really bookkeeping. That's all it is. Understand? And here's a nice thing I can tell you right now that you're going to like. Can I erase this right here? Got one person. In MATLAB, there's a command called FFT. And if you put FFT after you define the vector x, it'll give you the values of x and k. Boom. It'll just spit them out for you. And I'll give that to you for homework. I'll give you an example. But the nice thing is, you can check your answers in a heartbeat. Now let me just show you what I'm talking about. Math. Then I'll show you another trick you're going to like. So now, this is MATLAB. If I have a vector, let's just say I'm in the command line, and I get this and I say x equals, and I put solid brackets, and I put 1 space 2 space 1, or space 2, pardon me, 1, 2, 2, 1. The same thing we had, semicolon, so it doesn't repeat itself. This is MATLAB. If I want to see what the Dtft of this would be, it's actually the FFT, I simply I can just put, say, xk. I'm going to type capital X, small k. And I'm going to say equals, and then FFT of x. And bang, the next line will have x of k equal, and it'll show you, boom, 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 just what I put there. Follow me, class? And you will have the actual DFT of that. I'm going to let you do a few on MATLAB. I'm going to give you some to do. And you can do the inverse, too. If you want the inverse call it the inverse DTFT, which I put here, you can just put an I in front of there, IFFT. So if you put x, you want x, it would be equal to IFFT of, and then it would just be xk. That way you can see if you're right with any of the homework. Understand? It's an extremely obvious, simple thing to do. Now, there's one thing I have to tell you. For an FFT to work properly, it has to have 2 to the n values of x. Means it should be either 2, 4, right? 8, 16, 32, 64, 128, and so forth. If it doesn't have that value, what it does is add zeros. It's called zero padding. And that has an effect on the DFT that I'll get to later. I can't get to it right now in this class because I don't have the time. Are you with me in this class? Now, this is something, here's where we're actually into the computational portion. Now we can compute, using the computer, we can actually get real information about a real signal that we sample. Finite terms. We're sampling at a certain rate, twice the highest frequency of interest at least. Now I'm going to show you something that really helps. You may not see this, but you'll understand this when you do some of the homework. Now what I'm going to do is I'm going to establish a relationship between a continuous time Fourier transform, something that we have a pretty good feel for, and the DFT. So if we have a DFT, we can ultimately look at what the continuous time Fourier transform of that signal should be, approximately. And this is a real important point. This is not done in some books, but it's done, it's, in my opinion, very important. There is one condition for what I'm about to show you, though. It has to be sampled at a rate where the change in the value of x of n is very small. Not twice the highest frequency of interest, but x of n itself can't have a large change. So you got to be sampling at a very high rate. So there's no more than like 3 or 4% change in the value of x of n as you sample. Now there is an exception. That's about the 0, because you actually, if you hit 0, you cannot. And there's no percentage of 0 that will give you the next value. Let me show you what I'm going to do. First, I'm going to write the continuous time Fourier transform. I'm going to work to get the DFT. Write this down. So I say x of omega. This is one you'll like. Is x of t times e minus j omega t. dt. That's the definition of the continuous time Fourier transform. Now the next thing I'm going to do is take that, and I'm going to break this right here into a sum. I'm going to say what this really is going to be a summation from n equals minus infinity to infinity of the integral of n times the sampling interval to n plus 1 times the sampling interval of x of t times e to the minus j omega t dt. Now you all see that when I did this, I didn't change the value of anything. What I'm doing is what? I integrate, right, say n is minus 30. From minus 30 times ts, which is the sampling interval, let me put, this is the sampling time, really increment, time increment. It's a delta t. I'm just saying that now I'm going to go ahead and I've got a sum out here. It's going from minus infinity to infinity, and I'm integrating over small portions of the signal x of t and then adding them together. It's still legal. Do you all see that, class? How many see this right here? You almost know I'm doing that. You see this, and you're thinking that's Dtft, right? I'm working my way towards something that is going to look very familiar. Now I'm going to say this. Here's the caveat. I have to say x of nts is approximately equal to x of n plus 1 times ts. What I'm saying is there's very little change from the value of 1, from the value of here to here, of x of t. So it's sampling very fast. Understand? Now I'm going to go ahead and break this up. I'm going to say if that's the case, then I can say that this is really the summation here of n equals minus infinity to infinity. And now I can say x of nts. You all agree that if it's the same here as it is here, this is about a constant, and I can take it out in front. Do you agree with me there? Based on this assumption. All right? Then I have this times the integral from n ts to n plus 1 ts of e to the minus j omega t dt. This is actually kind of, first time I realized this, it was a long time ago, but it really made me see the usefulness of some of the comparisons that I was exposed to earlier. Now, is this a doable integral? Absolutely, isn't it? So what happens when I do that integral? I'll do it below here. Now I have the summation n equals minus infinity to infinity of x of n ts here. And then I have what? I have 1 over minus j omega when I integrate e to the minus j omega t dt. And I have e to the minus j omega times n plus 1 times ts minus e to the minus j omega times nts. You all see what I've done there? I've done the integration, then I stuck in the evaluation points nts and n plus 1 ts. You all see it, guys? Now, you all see I can factor out of both of these terms e to the minus j omega nts. Do you all see that? Because it exists here and here. So I can say that this is equal to the summation of n equals minus infinity to infinity x of nts, right there. And then I'm going to factor out the e to the minus j omega nts here, divided by minus j omega. And then I have e to the minus j omega ts here, minus 1. Please just take a look at that and realizing the only thing I'm doing is rearranging terms and factoring out the e to the minus j omega n ts out of that. You all see it, class? This is so important you do. Now, you realize that there's a minus sign, minus j there. I can take the minus sign up top, right? And since there's a minus, I'm going to reverse the order of these. Is that okay with everyone? In other words, I'm simply going to put the 1 first, and I'll put 1 minus e to the minus j omega ts here. I'm going to get rid of this minus. Follow me? Everybody okay with what I'm doing so far? Now, here's the last part of it. I can see here this sum is in n, right? You'll notice there's no n here. There's no n to j omega. Follow me? So I can take that in front of the sum, and I'm going to do that. I'm going to do it up here. This is a bit awkward, but I'm going to say now my x of omega here is equal to the 1 minus e to the minus j omega ts over j omega, and it's times this summation. N equals minus infinity to infinity of x of n ts times e to the minus j omega n ts. Are you with me, guys? Please watch this. This is really interesting. Are you with me? I just rearranged it to get it to there. I want to erase this because I'm going to need this portion of the board. The only thing I've done is take this, put it up there, and factor this and the j omega out in front. You all see it? Can everybody see this okay? All right. Don't look terrified. It's not that bad. Now we go ahead and we say we're going to bring it down to the finite domain. Now suppose we have a finite number of samples, and we're always going to start our sample count at n equals 0. Are you with me? So I'm going to go from 0 to some n minus 1, where capital N is the number of samples. So now I'm going to say that my x of omega is equal to 1 minus e to the minus j omega ts, right here, over j omega. And now I have a summation here where n is going to go from 0 to some n minus 1 of x, and I'm going to drop the ts. Remember how we drop it when we do discrete time sampling? We don't have the ts in the actual argument of x of n. Remember that class? We suppressed that. It's implied. So I can actually put square brackets x of n, and now it's going to be e to the minus j. But now this looks just like a DFT, doesn't it? Watch. I'm going to go ahead and put the omega NTS here, but watch, if that's a DFT, right? For a DFT, I erased it already, but for the DFT, the x of k was equal to the summation from n equals 0 to n minus 1 of x of n times the quantity e to the minus j times 2 pi over cap n to the nk. Y'all remember? I had that down a second ago, right? Now I come back to this, and I'm going to say the minus j omega nts is really equal to what? The minus j 2 pi over n, minus j 2 pi over n, keep going, nk, right? Follow me on this? Now what do you see happening? The j's go away. How's that? For starters, right? Y'all see the n's go away, small n? And then you see something. You see the omega here, right there, is actually equal to 2 pi k over capital N times Ts. So now you can say that instead of having x of omega, I have x of omega equals 2 pi k over nts, right there, and that's equal to 1 minus e to the minus j, and omega, right there, is 2 pi k over nts. So I'm over, I think I'm a minute over right now, but I can replace the omega here in ts by simply 2 pi k, right, over n here. And then the omega here is going to be 2 pi, it would be j 2 pi k over nts. And then, finally, this is the bottom one, instead of putting that there, I just put times x of k. Now, this is the bottom line. I get the Dtft, or the Dft, using any computer. Do you agree with this, class? I showed you how to do it math. I can take those values and just multiply them by this. Knowing the sampling time, knowing the number of samples, in this form, and I will get the Fourier transform. And it's very close. Matter of fact, it's amazingly close. Only it's going to be at discrete frequencies, where each of those frequencies is going to be 2 pi over nts times k. So the first frequency would be 0 and k is 0. The second frequency would be 2 pi over nts and so forth. Do you follow me on this? And it's an exact comparison. I'll give you some homework on this. Thank you. See you Wednesday. So is that going from